Welcome back students. Now we are going to study about water. Water is a compound of hydrogen and oxygen, and without water we cannot survive on earth. It is very important for our biological system also, so it becomes very important for us to study its chemistry. That means how it is prepared and what are its chemical and physical properties. What are hard water, what is soft water. So let's start. Water. Okay, now we are going to discuss about water. The first thing is what is structure of water actually. So you can see from here it has band structure. Oxygen connected with 2 hydrogen. Bond angle is 104.5 degrees Celsius with 2 lone pairs of electrons over oxygen. And this is a polar molecule because polarity is for this bond is in this direction. For this it is actually in this direction. For this bond it is in this direction, for this one it is in this direction. Then we have 2 lone pairs of electron. So overall polarity is like this. So it is a polar molecule. In water molecule, the 2 hydrogen atoms are bonded to 2 oxygen atoms by covalent bonds. The oxygen atom is sp3 hybridized actually. This is sp3 hybridized. Each of the covalent bonds are formed by axial overlap of 1s of hydrogen atoms and hybrid orbitals of O atom. The 2 bond pairs and 2 lone pairs of electron around the hydrogen atoms assume tetrahedral arrangement. So this is the basic structure actually. Tetrahedral how? So we have an oxygen, then a hydrogen, another hydrogen, then a lone pair, another lone pair. So it is something like tetrahedral geometry. Okay. Now due to relatively greater repulsion interaction of the lone pairs, erase all the things first. The bond angle is not 109 but 104. If it is a tetrahedral structure, then the bond angle must be 109, which is obvious for a tetrahedral structure. But because there are 2 lone pairs, okay, let me draw it once again. Oxygen, hydrogen, another hydrogen, then a lone pair, another lone pair. Now if it is a tetrahedral arrangement, the bond angle must be 109.28, but because there are 2 lone pairs of electron which cause bond pair repulsion, this bond angle is reduced to 104.5 degree. Now there is another thing, aggregation of water molecules. Okay, we are well aware of the term hydrogen bond. We have hydrogen, then oxygen, then hydrogen. This is partially positive charge, this is partially negative, this is partially positive. Similarly, we have another water molecule. This is partial positive, then partial negative, then partial positive. Now this partial positive hydrogen can attract the partial negative oxygen of another water molecule, and this type of attraction or the bonding is known as hydrogen bonding. And a given water molecule can form 3 hydrogen bonds, 1 by oxygen and 2 by hydrogens. So because of this excessive hydrogen bonding, the molecules aggregate together actually, which is known as aggregation of water molecules. In gaseous state, indivisible covalent molecule H2O exist as such. However, in liquid state, the large aggregates of water H2O units are formed because of their association through intermolecular hydrogen bonds. And the intermolecular hydrogen bonding is responsible for abnormally high freezing point, boiling point, heat of fizz and heat of vaporization as compared to the hydrides of other elements of oxygen family. So this is there is hydrogen bonding present between the water molecules, excessive hydrogen bonding, because of which they are most of the time present in the form of aggregation, and because of which their boiling point, freezing point, heat of fusion, heat of vaporization all are very high because of hydrogen bonding. Okay, now what happens that in ice, a solid state of water, ice is a solid state of water, we know very well. Each water molecule is tetrahedrally surrounded by 4 neighboring water molecules with their oxygen atoms occupying the corners of tetrahedron and the 4 hydrogen atoms around each oxygen atom. The 2 of the 4 hydrogen atoms are bounded by covalent bonds, whereas the 2 other are linked through hydrogen bonds as shown in the figure. Okay. So what happens that like this, we have oxygen, then we have hydrogen, then this is further surrounded by hydrogen, like this. So each water molecule is surrounded tetrahedrally by 4 other water molecules with oxygen at the corners of tetrahedron and hydrogen. Each oxygen atom is surrounded by 4 hydrogen atoms around each oxygen atom. So this is how the aggregation of water molecules in ice take place. They come together, there is excessive hydrogen bonding such that each water molecule is surrounded by 4 other water molecules tetrahedrally, and each oxygen atom is surrounded by 4 hydrogen atoms, and because of which a close packed structure is formed, which is known as ice. Now what happened, due to open case like structure, the structure is known as open case like structure, ice has relatively larger volume for given mass of liquid water. Okay, if we have liquid water molecules, they would be close enough, but if they are arranged in the form of ice, what would happen? You can see from here only. Now they are covering larger area. So you can see that for 3 water molecules, here the area was less, here the area is high. So what happens, because of which overall what is density? Density is mass upon volume. Mass is same for those, but volume is increasing, because of which the density of ice gets decreased and now it can float over water. Okay. As the temperature is raised beyond 273 Kelvin, the open case structure of ice starts breaking down because of cleavage of some hydrogen bonds, and ice starts melting. The breaking of hydrogen bonds causes aggregation of water molecules to have closer, resulting in the decrease in volume and thereby increase in density. And this continues up to 277 Kelvin, where the density becomes maximum, or we can say 4 degrees Celsius. Beyond 4 degrees Celsius or 277 Kelvin, more hydrogen bonds cleave and expansion of liquid water starts occurring due to the increase in kinetic energy of the molecules, and therefore density starts decreasing. So we have ice. When we melt it up to 277 or 4 degrees Celsius, we have water with maximum density. And beyond this, density further decreases. So maximum density of water is at 4 degrees Celsius. Okay. So this is how the water starts melting and its density changes. Okay. But still, at any point of time, the density of water is greater than that of ice. So maximum at 273. Now there is something known as heavy water. We are very well aware of the fact that there are hydrogen, protium, deuterium and tritium. 3 isotopes of hydrogen. Tritium is radioactive, so it is not stable, but if water is formed by a deuterium molecule, it is known as heavy water. Heavy water is the oxide of heavy hydrogen, that is deuterium, and it is also called as deuterium oxide, and it is represented by formula D2O or H2O. And how it is used? Actually, heavy water is used as a neutron moderator. It is the substance which are used for slowing down the speed of neutron are called neutron moderator, and heavy water is used for this purpose in nuclear reactors. Next is, it is used for preparation of deuterium. Actually, heavy water on electrolysis by its composition, a metal produces deuterium. We are very well known of the fact that if water is electrolyzed, we will get hydrogen. So if heavy water is electrolyzed, we get deuterium. It's so simple. Okay. Now next use is that it is used as a tracer of the compound. Heavy water is commonly used as a tracer compound for studying various reaction mechanisms. It is also used for studying the structure of some oxo acids of phosphorus like H3PO2 and H3PO3 as to determine the number of ionizable hydrogen atoms. Now there is a term hard and soft water actually. Okay, if the water can be classified into categories depending upon its behavior toward the soap solution, and these are soft water and hard water. Soft water is that water which produces leather with soap solution radially. Distilled water and rainwater are the examples of soft water. Now hard water is that one which do not produce leather with the soap. and example is sea water, tap water, common examples of hard water. And the hardness of water is basically due to dissolved impurity like bicarbonates, chlorides and sulfides of calcium and magnesium. We can say that whenever magnesium salts and calcium salts are present in water in dissolved form, the water do not form leather with soap, and soap do not work with that water, and that water is known as hard water. Okay, and hard water does not produce leather with the soap easily. Why? Because the cation calcium and magnesium ion present in hard water react with soap to form precipitate of calcium and magnesium. We can see actually a soap molecule is something like this. When it comes in contact with calcium ion present in water, it forms RCOOCA2 negative, which gets accumulated in the form of scum, and that is why the soap does not work, do not produce leather. Okay. Now hardness is basically of two types, temporary hardness and permanently hardness. Actually temporary hardness is due to the presence of soluble bicarbonates of calcium and magnesium. Okay, we have told you that there are two types of salt, bicarbonates and chloride. So if bicarbonate is present, it is known as temporary hardness, and if chlorides are present, they are known as permanent hardness. So temporary hardness is due to presence of soluble bicarbonates of calcium and magnesium, and such water is also said to possess carbonate hardness. The term temporary hardness indicates that most of the hardness can be removed by simply boiling the water. The bicarbonates of calcium and magnesium are formed in water by dissolution of carbonates of calcium and magnesium in the presence of atmospheric carbon dioxide. Okay. And another type of hardness is permanent hardness, which is basically present due to chlorides and sulfides of calcium. So if carbonates are present, they are temporary hardness, and if chlorides and sulfides are present, it is permanent hardness, which cannot be removed by just boiling. So calcium carbonate will produce temporary hardness, and calcium ClCO2, calcium chloride or calcium sulfate will produce permanent hardness. This hardness cannot be removed by just boiling water. Okay, so the first thing is removal of hardness, and the first is removal of temporary hardness. So we have told you that temporary hardness can be removed by just boiling the water, okay, for 15 minutes. Consequently, the bicarbonates of calcium and magnesium present in water decompose into their soluble carbonates, which settle down at the bottom of the tank as precipitate, which are removed by filtration simply. Okay, now removal of permanent hardness is little bit tricky. It cannot be removed by just boiling. So there are various methods which are used for removal of permanent hardness, and the first method is addition of washing soda. Okay, so if we add washing soda, what would happen? That you can see from here, we have what happens that let's say we have calcium or magnesium ions, then this ion reacts with carbonate salt, which was present as hardness, and results in formation of magnesium metal carbonate. If I take the example, then I had calcium, 2 positive ion, it reacted with CO3 2 negative of washing soda to produce calcium carbonate, and it will precipitate out, and then which can be separated in by filtration simply. Another method is addition of sodium polyphosphate, polymetaphosphate, or which is also known as Calogan process. In this, what is done? Let's say we have calcium salt present in this, then into this we add Na2, Na4, PO3 whole 6, which is sodium polymetaphosphate, or we can see it is Calgon. Then this Calgon actually results in formation of a compound Na2, sodium is replaced by calcium, then we get PO3 6, and this is soluble. So this is how calcium is removed. Similar can be used for removal of magnesium salts also, same would be the reaction, and at the end we'll get Na2 Mg whole twice PO3 6. This is also soluble. So in this method, calcium and magnesium ions are rendered ineffective. We make them ineffective by addition of sodium polymetaphosphate, the trace name of which is Calogan. Okay, in the general formula of sodium polymetaphosphate is, actually if we talk about the general formula, it is like this. Okay, where n is sometime we can say as larger as 1000, so we will write it here n, and it is maybe larger than 10,000. So this is calogen is added, and the calcium and magnesium salts are converted into soluble salt. Okay, and this complex of calcium and magnesium so formed remain dissolved in water, but they do not cause hindrance in the formation of leather. Okay, next is actually an ion exchange method. In this, okay, so we use zeolites. So these are the complex inorganic salts like hydrated sodium aluminate silicate, this is the formula, which have interesting property of exchanging cations such as calcium and magnesium ions in hard water and sodium ion. This complex salt is also known as zeolite, which can be either a naturally occurring or an artificially synthesized substance. So what we do, we take sodium zeolite, Na2Z, we have sodium zeolite. This sodium zeolite is when reacts with salt of magnesium or sodium, we get Mz. This is exchange resin, and along with this we get sodium chloride. So what is done, this sodium has been exchanged with magnesium. Actually we have exchanged sodium with magnesium, that is why it is known as ion exchange method. And the formula of Z is obviously most of the time Al2Si2O3H2O, here sodium, you can see from here, and this sodium salt is exchanged with magnesium. And if the process is continued, the zeolites gets used up because of its conversion into calcium and magnesium zeolites. The used up resin is actually regenerated, allowing it about 10% solution of sodium chloride to stand with it, and the following reaction takes place. That this was actually the zeolite formed. When it is allowed to stand, it reacts with sodium chloride further to form Na2Z, and the resin is regenerated to form and we get magnesium chloride. So that's why we have to remove it, because if we just dissolve our ion exchange agent and we leave it for the long time, the salt will get regenerated. So we have to remove it after a certain interval of time. Now there is a salt problem, that which of the following will not produce a hard water? Saturation of magnesium, we add magnesium carbonate, we get Mg2 positive. With calcium we get calcium 2 positive. With sodium we'll get sodium positive, and here we'll get calcium positive. Actually the hardness is because of dissolved salt of magnesium and calcium only, and not of sodium. So C is the correct option, that addition of sodium sulfate will not cause hardness into water. So now we are aware of chemical and physical behavior of water, and we also know what is hard water, what is soft water, and how to remove hardness of a water, and we are also aware of heavy water. In our next video we are going to study about another compound of hydrogen and oxygen, that is hydrogen peroxide. So stay tuned.